Assalamualaikum and hi, my name is Nur Hanani from Group 33 and together with my teammate Arif Kamal and Eng Zongjian, we're going to talk about the modification on bus to overcome aerodynamic drag effect under CFD project. In Malaysia, buses are commonly used for long journeys between states of 100 to 500 kilometers. Costing as low as 10 ringgit per ride, buses become one of the public's preferred mode of transportation. However, in the automotive industry, fuel consumption still continues to be a major problem. Even though there have been various approaches to tackle this issue, reducing the aerodynamic drag has the most significant impact on the fuel consumption. Thus, in this project, we primarily focus on the aerodynamic of the existing bus and compare it to the one that has been modified with enhanced exterior stylings with the help of CFD software. The real question is, how will reducing aerodynamic drag impact on fuel consumption? To answer to that, we made a hypothesis: less drag, less force needed to move the bus, hence lowering the fuel consumption. The purpose of this project is, firstly, to identify how reducing aerodynamic drag impact on fuel consumption, and second, to reduce aerodynamic drag by modifying the existing bus, and last one, to compare the drag coefficient of existing bus and modified bus in 3 different speeds, which is 80, 100 and 120 km per hour.
My name is Eng Zongjian and now I'll talk about the modifications we did on our bus model. First of all, for the front face, the front end of the bus is filleted into 150mm radius to provide a curved section. This is to minimize the stagnation pressure regions and improve the flow on the bus. As for the sidewall, in order to reduce air separation, a wavy and curvy pattern of the sidewall is designed. This aerodynamic shape will minimize the amount of drag caused by air passing through the bus. Lastly, for the underbody, the bottom front face is filleted to 120mm radius of curvature to allow the air passes through with lesser drag. This will result in a streamlined and smooth flow underneath the bus.
Assalamualaikum, my name is Muhammad Arif Kamal. I'm going to explain about CFD procedures and simulations. Okay, first step, first we must open the NC's workbench and then select the fluid flow fluid. Okay. To do this fluid flow fluid is for airflow simulation, as our objective is to analyze modified bus model, and there are 5 steps or section needs to be completed before we get the results. Okay, for the first section, which is geometry, you can open this script. As you can see here, is here modified bus model. So we open here. Then we must do the enclosure for the air fluid domain. Okay, next we can close the geometry. Go to next section, which is mesh. We can see our mesh here. We just render this mesh using default sizing, which is 1 meter. And we also specify the velocity inlet and also the pressure outlet of the enclosure for the air domain. Next, for the setup, okay, here we set the model as viscous model standard K epsilon, standard K epsilon model. And then for the boundary condition that we input. We put 80, 100 and 120 km per hour for the bus model. For the outlet, just put 0 pressure. That's it. And then at the record definition, we put drag and lift coefficient. To let the software calculate for us. And then we calculate, initialize and calculate for 50 iterations to get the results. That's all for the setup part. At the result, we can select the pressure velocity contour around the bus, and also we can simulate the streamline of the velocity. So as for the contour, okay, that's all from me. Thank you.
As you can see from the picture down below, it is a static pressure plot of the existing and modified bus at speed of 120 km per hour. The frontal area of these two buses is under maximum pressure due to stagnation. This pressure difference can lead to a high pressure drag on the bus body. However, the pressure on the frontal area of the modified bus experiences lower pressure than the existing bus. This is intended to minimize the pressure drag acting on the bus. Next is velocity contour. As you can see, the flow separation at the front top part of the modified bus has reduced compared to the existing one. As the front part is designed aerodynamically, air may flow freely through it. Also, the curved end at the back side of the modified bus leads to increase in velocity flow, which this helps to reduce drag. The most important part is velocity streamline. The curved end at the bottom part of the bus has improved the flow pattern. Observing the modified bus streamlines, it is clear that the flow is much more streamlined and the wake region behind the bus has decreased drastically, resulting in significant reduction in the coefficient drag for the modified bus when compared to the existing bus.
Now I'd like to talk about the drag coefficient. For the speed of 80 km per hour, the drag coefficient for the existing bus model is 0.4196, while the drag coefficient for the modified bus is 0.2098. The reduction is 50%. As for the speed of 100 km per hour, the coefficient for existing bus model is 0.65963, and for the modified bus it is 0.3104. The reduction is 52.7%. Lastly, for the 120 km per hour, the coefficient for existing bus model is 0.9272, while the coefficient for the modified bus is 0.4454. The reduction is 52%. Now I'd like to talk about the fuel consumption. The percentage of fuel reduction is about 60% of the percentage of total drag reduction. As the result, the fuel saving for the speed of 80 km per hour is 30%, while for the 100 km per hour it is 31.62%, and lastly for the 120 km per hour it is 31.2%. Lastly, as for the conclusion, the streamlined design is crucial for long-distance high-speed bus. The velocities given to the fluent analysis are 80, 100 and 120 km per hour. The modified bus has the lowest coefficient drag, resulting a percentage reduction up to 52.7%, saving 31.62 average of fuel consumption. The aim of the project has achieved.